Okay, we're going to begin by taking a quick look at one of the homework problems. Aileen, what number was this? And it said in 1 year the number was 425, and that was in year 2010, and then 2011. Okay, 2011. And what we wanted to know here was the percent growth rate, I think. Okay. All right, so here I'm going to make a very open admission to you guys. I've covered the exponential growth section, I think every semester that I've taught this class, and I think I've taught it about 4 or 5 times. But there were a few problems in the notes that we did on Monday that I've never done before. And some of these problems I didn't quite present it the right way, and some of them were maybe a little bit more complicated than what we had prepared you to answer. And so I know that there was some confusion on Monday, and I apologize. Just the lesson plan wasn't as good as I wanted it to be. And so this question right here we're going to answer right now, but I'm going to take it off the table in terms of the test. I'm not going to expect you to find percent growth rate on the test. If you want to know what I am going to expect on the test, the best source is the sample test problems at the end of this packet. If you can do the sample test problems with regards to this exponential growth stuff, you're going to be in good shape, okay? But let's give this one a shot. So it turns out that that what we want to do here is we're going to take the new number, we're going to divide it by the old number, and we're going to subtract 1 from that. It's a crazy formula. I'm not going to ask you to memorize it. I'm never going to ask you to use it. But just so you can see where the answer in the back of the book came from. Yes? Yeah, absolutely. That's equivalent to what we've got here. Yeah, it's the same. So let's do this. So what's the new number? 463. That's the latest one. And 425. And then we're going to subtract 1. And so if we just type this thing into our calculators, you're going to get 0.089 and change. And then we know that's 8.9%. We did it a little bit. Yeah. But anyway, I'm showing this question. Aileen asked about it, but I'm showing it to let you know that I'm not going to ask you to do this again. There were some formulas that I didn't quite think all the way through when I made this lesson plan when Caitlin and I were looking at it. So anyway, I'm taking that off the table. Okay. All right. So let's take a look at our calendar. And in the calendar, we see we have Fibonacci numbers in nature today. We're just going to continue. We started some of the Fibonacci stuff last class, so we'll continue it. And then the apportionment projects were due on Monday. I'm going to give you guys feedback today for everybody that got it to me by Monday. I'll give you feedback today during the group work time of this class. And then our next class is our review day, and then the test is after that. What's happening this coming Monday? Because it doesn't appear here in the calendar. Veterans Day. So there are no day classes this coming Monday. So the next time we see each other is going to be a full week from now. You're going to cry yourself to sleep every night between now and then until finally we meet again Wednesday to do our review. And then Friday is the next Monday is our test. Now let me also say this. During the fall semester, every full-time faculty member here at GCC has a student evaluation happen. And you guys have probably filled out these bubble sheets with a lot of questions on them. Maybe there's some other comments you can write in and stuff like that. So I can tell you that that is happening for me in this class Wednesday, 1 week from today. It'll happen towards the start of the review period, and then we'll have the whole period to review. And so I'm just going to put it out there. I know some students see review day and decide, oh, I don't need to go because there's not going to be anything new. I don't think that's a good strategy to have. I think that folks can really improve their performance on the upcoming test by showing up on the review day and working with your neighbors and working with me to answer questions. Additionally, if you don't show up for me on Wednesday next week, you cannot fill that bubble sheet in and you can't give me the feedback that I'm going to ask for you guys. And so I'm really hoping that people will come on that Wednesday. I can't give you this bubble sheet any other time. It's got to be all at the same time. So please come and we can review stuff and you can give me some feedback. Any questions on the calendar? Okay, so let's take a look back at the notes and we'll remind ourselves about this whole bee problem. So there was this really strange way in which bees reproduce. A female bee has how many parents? Female bee has 2 parents, a mother and a father. but a male bee has only one parent, and it's always a mother. And that's true, it's just the way that it works. And so what you guys did for me was you filled in the family tree for that one single male bee at the top of this chart. And then you started counting the number of bees that we had, 5, 8, 13, 21. And then you looked for a pattern. So let's write down the pattern in English. What's the pattern with these numbers here in purple? Current generation plus previous generation gives you the next generation. See if we buy that. If you take 5 and 8 and add them up, what do you get? 13. If you take 8 and 13 and add them up, 21. That's the pattern in plain English. If you want to find a number, you add the two previous numbers. Super. Okay, so let's go on to the next page. So hopefully you filled in most of this last time. I think we just wanted to remind ourselves of what those numbers were. And we'll begin here with number 2. Jeremy. Great, thank you. Chad? Okay, so everybody's clear on that, right? We're just calling these guys by the number that they are in the list, right? And those are the Fibonacci, F for Fibonacci. Okay, so let's go to number 3. We'll go to the back to Stephen. Okay, so let's find F8. I think you actually have it in the table already, but let's just look at the numbers that are on this page. If I want to get F8, what 2 numbers do I need to add? F6 and F7, just the 2 previous ones. So 8 and 13 is 21. That's the number you filled in yesterday or on Monday. And then if you want to find F9, which 2 numbers do you add up? F8 and F7. So F8 we just found is 21 plus 13 is 34. Any questions on getting the 34? Everybody see where that 34 comes from? Okay, and then the next number, what do we add? 34 and 21. So F10 is 55. That's it. So let's move to 4. Sam? Okay, so all we're going to do is translate Chad's sentence in English into sequence notation. So he said, if you want to get the next number, you add the current number to the previous number. So I'm going to start here, and I'm going to say, okay, what if we decide that we're going to call the current number let's see. I'm going to call the previous number Fn. If that's the previous number, then what's the current number? Is n plus 1, yes? Previous one, current one, and then finally, that's going to give us what's the number for the next, the name for the next one. Is it n minus 1? I think it's n plus 2, yeah. So I'll write, so this here was the previous one. This is the current. And this is the next, and it's the next one because it's one more out than the current one. One more than the n plus 1 gives you the n plus 2. There are other ways to write this. I'm just going to put this in parentheses. You could also have said, oh, if you want Fn, you take Fn minus 1 and you add Fn minus 2. Add the number that was 1 back and the number that was 2 back. They both say exactly the same thing. So it makes no difference which one feels natural to you. Just pick one. Let's go to Casey for the 2. Okay, so we do need to have 2 starting numbers in order to use this process, because this process relies on adding the 2 previous numbers. So you got to have 2 to start with. 1 and 1 are our first 2 numbers. Okay, we'll go to Griffin. If you're interested, you can look it up. It turns out it is possible to find, say, for example, the 39th Fibonacci number without knowing the first 38. There's a formula. It's complicated. You can look it up that you can just plug in 39 for the n, and it will spit out whatever this massive number is, 63,245,000, all that stuff. We're not going to talk about it, but it exists. But questions that I would like you to be able to answer are something like this. If I tell you the 39th number is this 63 million and change, and then the 40th number is this 102 million and change, how would we find the 41st number? Add those two up. Go ahead. So find F41 for us, and also find F38. Think about how to do that with your neighbors. Anybody else get that 39 million and change? Good. So if we're going ahead in this list, we know we need to add two numbers together. But if we're going backwards, it's just the opposite operation. Subtract the two numbers. Questions on either of those? Okay, let's move on. Griffin, did you read? You did. Evan, 5. Okay, so here is what we had until Fibonacci introduced the Arabic numerals to us. So how do I add these numbers together? I have no idea. I mean, like, all right, so first you guys probably know, what does the I mean? I is 1V, it's 5, and X is 10. So is it as simple as just saying, okay, that's 1 plus 10 is 11? Is it as simple as that? The answer is no, because why? That isn't really 10. That's part of a bigger symbol called IX. What is IX? It's 9. So you can't just straight look at every X and say, oh, every X is 10. It's not. These two symbols belong together. And so it's not really this 1 plus this 10. It's really 1 plus 9. So really hard to do arithmetic using Roman numerals. Okay, but the first number is really 18. And the second number is, that's 20 plus the 9 is 29. And it's really easy to add 18 and 29 when it's written that way. So we have Fibonacci to thank for bringing Arabic numerals out this way. Great. Let's keep going to Ed, the work. Thank you, Mary. Okay, so rabbits are known for jumping and they're known for procreating. And so this is an example of rabbits procreating. And we're not going to go through the whole process here, but let's just get started. You don't need to write this part, but that was the problem that Fibonacci posed. And so we start off with, I'll say here, number of the month. And then we're going to fill in as needed. So at the very beginning of the month, how many pairs of rabbits do we have? 1. All right, so then I'm going to call this guy here number of newborns, number of young pairs of rabbits. So it's 1. And then at some point, these rabbits become mature enough to procreate. And so I'm going to have a new column for number of adults. But how many adult rabbits are there right now? Those are baby rabbits. There are no adults yet. We start off with just 1 pair of baby rabbits and no adult rabbits. And so then I'm going to put here total number of rabbits. All of these are pairs, by the way. I'm saying rabbits, but I always mean pairs of rabbits. So there we have 1 pair of rabbits. They are baby rabbits, no problem. Then we go to month number 1, and that pair of newborns becomes older. And so they're not baby rabbits anymore. They are now adult rabbits. Yes? So we still have 1, but what's different about that 1 pair? They're now adults. So that pair of adult rabbits, some candlelight, some nice music, and what happens the next month? They multiply. And so that 1 pair of adult rabbits gives us a new pair of baby rabbits right there. How many adult rabbits do we still have there? How many pairs? How many pairs of rabbits? We have one pair of adults rabbits, the same from before. So now how many pairs of rabbits are there? There are two. One baby pair, one adult pair. Yeah? Okay, next month. Okay, are there any adult rabbits from the previous month that are going to give us new babies? Yes, how many adult pairs were there? One. So that one pair of adults is still going strong, and they give us another pair of baby rabbits. Casey, why are there two adults now? That's right. The baby rabbits from last month are now adult, plus the adults that we had. So maybe in a different color here, we'll say that one and that one gives us two. So how many pairs of rabbits do I have now? Three. Let's do one more. Fourth month. Okay, I'm looking for how many newborns I get. It has to do with how many adult rabbits I had the previous month. How many adult rabbits did we have last month? We had two. So each of those gives us another pair of babies. So that 2 gets copied over there. In terms of the number of adults that we have, it's 3 because you had 2 adults and then you had one pair of babies that is about to become adult. And so we have 3 pairs of adults now. How many pairs altogether? 5. And those numbers right there should look familiar. 1, 1, 2, 3, 5. It's the Fibonacci numbers. We saw them coming up in terms of bees and a family tree. This is different, but it's the same exact set of numbers. Okay, good, good. Let's move to the next page. 7. The pictures are probably going to be easier to see up on the board in color. Let's go to Brandon, 7. Okay, so we've got a few daisies up here on the board. If you count, I don't know if you can see, but there are little numbers on the daisies on your copy. But if you count all the petals of the daisies, anybody read that number? It's 13. 13 is one of our special numbers now. 13 is in our list. Then let's look at this next daisy. It's going to be really hard to read. There's many more petals there, but it says 21 up there. 21 is another Fibonacci number. And then here's another daisy with even more petals. And what's the, is 34. Now, I'm not saying that every daisy that you go out and look at, if you count, you're going to find one of these Fibonacci numbers, but it happens more often than it would if it was just a coincidence. So oftentimes, the number of petals in a daisy is a Fibonacci number. And then we've got these kind of pine cone things, right? If you look at the bottom of a pine cone, you guys have seen pine cones, right? And so what we're going to do here is count spirals. Now, this is going to be really hard to see in your black and white and blurry image, so I'll try to make it a little bit clearer up here. But for example, if I start, let's see, where's the number 1? If I start right here and I just draw along one of these spirals of I don't know what those little things on the pine cone are called, but if I just spiral out, and I'm going to count how many things like that there are. So that's 1, and then I could come along a completely different spiral out here, and that one ends out there, and that's 2, and you can just count how many spirals you get. I don't know if you can read it, but do you see how many spirals there are? It's really hard to see. I think it's an 8 right up there. There are 8 spirals if you go counterclockwise. The next one is exactly the same picture, but now we're going to look at the spirals going clockwise. So for example, looking at this path, so these spirals are shorter and there's going to be more of them. Can you read how many there are going the other way? It's 13. 8 and 13 are both Fibonacci numbers. And if you want bigger Fibonacci numbers in terms of counting spirals, we need a different kind of thing. What does this say? Sunflower, is that what it is? Yeah. And so if you count, now these are teeny tiny things in here. I think they're called florets. Is that the right? I'm not sure if that's the right word. But what we are looking at down there is this guy zoomed in. So if you really zoom in, you get this kind of shape and you see these spirals here. And can you read how many? First one is a 21. There's 21 spirals down there. Another Fibonacci number. And going the other direction, it's 34. It's the next Fibonacci number. It's just really weird how often it comes up. So that's just a smattering of places, but if you're interested in this, just go look up Fibonacci numbers and you will see them all over the place. All right, so group work, and then we'll come back, and then more group work. So we'll start here with Aileen, fill in. Okay, and then we'll go to Jake. Okay, so we're going to do this page together, and then you guys are going to do the heart of it on the next page in your groups. Okay, so the first two Fibonacci numbers are 1 and 1. What's the next one? 1 plus 1 is 2, and then 3. All right, so we're filling these guys in. So everybody fill in this column. Okay. And now we're really going to want to use the calculator to fill in the other column. So before you continue to the next page, let me just do one of these examples in the right-hand column. I'm going to pick, I don't know which one. Let's pick this guy right here. No, I'll do the last one right here. F8 over F7, you don't see that?
We don't have F8, it's on the next page. F8 is on the next page. Here, I goes to F7.
Oh, we don't have F8, right. Of course we don't. Oh, okay. All right, so 21 is on your next page. Okay, no problem. But this tells me to take F8 and divide by F7. How much is F8? It's 21. F7 is 13. And we're just going to divide them. And we're always going to divide in that order with the next number over the previous number. And so somebody with a calculator? 6, 1, 5, 3, 8. Yeah, I'm going to ask you guys to write down 5 digits after the decimal place for every one of these, okay? So make sure you write enough, otherwise you're going to miss the point when we get there. So here's my suggestion. Fill in the first column together. Make sure everybody has the same numbers in the first column, and then divvy up the work in the second column, right? You don't all have to do every one of these divisions. What did we end up getting here when we were dividing all these quotients? What was the last one? 3. And how about when you did 30 divided by 29? Same thing. Same thing. Now, they weren't all the same thing going up, but they were getting closer and closer. They were kind of honing in on this magical number, right? Even as the Fibonacci numbers get huge, right? These are huge numbers that we're looking at. 100 million is this 40th Fibonacci number. It's really big, but when you divide it by the previous one, you end up getting this very strange 1.61803 every time. It's really weird. 8, I think we are around to Lila. Okay, so you guys have seen some Greek letter before to represent a really famous number in math. What Greek letter have you seen that represents a number? It's pi, right? And you guys know that pi is around 3.14. Anybody know more? You're missing something. So 159, yep. 6, 5, 3, 5. You guys know, you know these. So it is not, it's not uncommon to use a Greek letter to represent a famous number. Here is another Greek letter to represent another famous number, 1.618. All right, let's go to the next page. Given that the 499th Fibonacci number is this massive, massive number, right? 8.6 times 10 to the 103rd power. It's huge. It's got over 100 digits in it. I want to find an approximate value for the 500th Fibonacci number. Now, haven't we done this already? How do you get the next Fibonacci number? You add the previous 2. Can we do that? Can we add the previous 2 in this case? Why not? It's not the arithmetic that's the problem. You don't have the previous 2. All you have is one number, the 499th. If I were feeling generous and I also gave you the 498th number, then you could just add them together. But I'm not feeling generous. I'm just going to give you the 1. Very stingy. So here's how we're going to use this fact. So here's something that I want you to believe. If you take the 500th number and you divide it by the 499th number, without even knowing what the 500th number is, do you have a guess as to what we're going to get? 1.68. Oh, what did I miss? 1.61803. Right? We're going to get that. So yeah, so let's move this F499 over to the other side by multiplying. And what we see is that the 500th number is going to be really close to 1.61803 times the 499th number. Yes? And it's not going to be exact because the 1.61803 is not exact, but it's going to be close enough. And so this is the kind of thing I'm going to ask you to be able to do on a test. And so if we want to type in this craziness on the calculator, I'll show it to you here on the scientific or on the graphing one. And then I can walk around and look at your individual calculators if you're having trouble with this. So here's what we do, 1.61803, type in all 5 digits there, times, and now what was the 499th? 8.6, and then times 10 to the 103, I just type it, times 10, and then for me this little up arrow here is the power button, to the 103. Okay, it's kind of big. So what are we expected to do here? I'll give you one where it won't overflow. How about we say that? If I really want to know what this is going to be, I'm just going to change, oops, second, enter. I'm just going to get rid of this 10 business. It's that times 10 to the 103. Right, I just didn't put the 10 to the 103 in here. So 13.94 times 10 to the 103. But I'll give you one on the test. If I give you one on the test, I'll give you one where it won't overflow. And just to make sure we believe that, go back in your chart. What was the 19th Fibonacci number? How much? 4181. I'm going to take 4181, a single Fibonacci number. I'm going to multiply by this magical golden ratio, and I'm going to get something really close to the next Fibonacci number. You guys know the next Fibonacci number because you have it on your chart. 67, what is it? 65? 6765. It's not going to be perfect, but if I just said, hey, round this to the nearest integer, you'd get 6765, right? And if I wanted it to be better, then, oh, I didn't even type that in right. It's 1.61803, right? Okay, even better. 6765 within 2/100ths of the right answer, okay? All right, moving on to 9. Where are we now? I lost it. Kate. Okay, so it's kind of a weird question, but the question arose back in ancient Greece. So, you know, like 2,500 years ago, they didn't have like Wii's to play with back then. So they asked questions like this, like what's the prettiest way to cut up a line segment? So for example, you could decide you're going to cut the line segment like out there. And you might say, oh, that's the nicest way to cut the line segment. Maybe some of you are thinking the middle is the nicest way to cut the line segment. Maybe some people are kind of like, you know, 2/3 of the way in. There are a lot of different ways I could cut this line segment into 2 smaller pieces. The Greeks wanted to know what the prettiest way was. The Greeks were really interested in questions about aesthetics, and this was a natural question for them to ask. So someone decided that the most aesthetically pleasing way to divide the line is to cut it in such a way that if you take the length of the short piece divided by the length of the medium piece, it's the same ratio as the length of the medium piece to the whole piece. Let's translate that into some symbols. The short piece in this example is which of these? Is 1. So this guy becomes 1 over medium piece, x, and we want that to be the same ratio as the medium piece, still x, divided by the length of the whole line, 1 plus x. So we can translate the Greeks' suggestion into this modern notation. Now this is going to take us afield from stuff that I'm going to expect you to do, but if we cross multiply, and I think some of you have seen that phrase before in some algebra class, then what it says is 1 times 1 plus x is equal to x times x. multiply the two diagonals, and it's still equal. 1 times anything is just itself, so I'm not going to write the 1 anymore. Yes? Anybody know the name of an equation where the highest power is squared? Starts with a Q. That's a quadratic equation. There's a whole branch of algebra that studies how to solve quadratic equations. Make one side 0 is almost always the right thing to do first. And then there's something called the quadratic formula. Anybody remember it? Evan? Evan remembers doing it. Evan has heard of the quadratic formula. Yeah, and I bet many more of you have too. Negative b plus or minus square root b squared minus 4ac all divided by 2a. Right. So you can use that formula, whatever it means, and solve this equation. I'm just going to tell you what the answer is because I'm not going to ask you to do that here. But this is the answer. 1 plus root 5 over 2 is the solution to this problem, to that equation. Okay, let's see if we can type this on the calculator, and then we're going to act surprised. 1 plus root 5, 1 plus, so you don't need to worry about this either. 1 plus root 5 divided by 2. I had to put an extra set of parentheses because the numerator is complicated. I didn't type it in right. 1 plus root 5. And what do we get? What is that called? That's the golden ratio, or phi, 1.618. So what the Greeks figured is that the best way to cut up a line is to cut it up in such a way that this piece right here is 1.618 times the short piece. The medium piece to the short piece is 1.618 to 1. That's the best way to cut it up. Okay, let's go to 10. Damien. Thank you. Barb, 11. Okay, so this 1.6, I'm just going to round it pretty roughly at 1.6, pops up all the time because it's pleasing to the eye. So if you take out a credit card and you measure the two sides, this side is going to be about 1.6 times as long as the other side. I'm not saying they're going to be 1 inch and 1.6, but it might be like 2 inches and whatever 1.6 of that guy is. 2 inches and, I'm doing this right, 3.2. It's just going to be 1.6 times the shorter side. Like literally, go later on, take out a credit card and get your ruler out and calculate the ratio, and I bet you get something really close to 1.6. And if you have a laptop somewhere handy, measure the short side, measure the long side, divide, and you're going to get something pretty close to this 1.6. What's going on in this picture? I have no space needles. So my guess is that this guy right here is about 1.6 times as long as that guy. The next picture, one of the ancient pyramids from Egypt. I can't read what's going on in there, but apparently something is 1.6 times something else. What's the name of this guy? Parthenon, right? Parthenon from ancient Greece. I forget where the 1.6s are here. I think this to this, something like that, 1.6. And then what's the name of her? Mona Lisa, and so people have drawn in rectangles. Now you can argue that the rectangles were just arbitrarily drawn in to make 1.6s. You can make that case. But if you accept that her face is essentially contained in that rectangle, and you start doing some measurements, you'll find that the long side is about 1.6 times the shorter side. Okay. Group activity is right here. See how far you can get in this. And I'm going to keep talking to people about the projects.